All right, has everyone finished reading the problem? All right, so this is the first example. So notice here that every row is sorted, right? And every column is sorted, right? And your goal is to check if a given target exists in the matrix. Any thoughts? Okay. So you brought up a good point. So you're saying if the rows are sorted, and also the upper rows are smaller than the lower rows, right? So if you had something like,
if you had something like,
instead of 2 here, you start with 16, right? And then this is
right.
17 or something. Then this is 19. Then this has to be like something greater than 19. If you have something like this, where it's sorted from the top left to bottom right, then how would you do binary search?
So you can split it in half, and then you check the last element of the first half, and then the first element of the second half, and you check whether it's like bigger or smaller.
Okay, but how do you divide this into like, this is a 5 by 5 matrix, right? So are you going to consider everything like in this half? This is like your left, and this is your right half, or?
Yeah, I mean, the way I would have done it probably is if you split however many inner arrays, whatever, how many rows you want to call them there are in the grid. If there's an odd number, then you just round it, and then you continuously do that until like split them in half, call it recursively, until you eventually find your target.
Okay, so my recommendation would be, if you wanted to do binary search, instead of try to split the entire matrix into 2 halves, maybe you can first do a binary search on just the first row, or on this first column, right, to figure out which row your target is in.
I was gonna suggest that.
Yeah, because once you figure out which row you're in, then you can do another binary search to figure out which column you're in.
Yeah.
Right, and I think this approach also works in our original problem, where it's not sorted from top left to bottom right, right? Where only each row is sorted individually and each column is sorted individually. Still, you can apply this binary search, right? So if the target is 5, now you can say, okay, so is it in the first row? Right? You can do a binary search just in this row and see if 5 is there, right? If 5 is not there, then you do a binary search here, right? And if 5 were not there, then you would continue, right? So this could still work, right? The binary search can still work even in this problem. It's just that if we have to be careful about our runtime analysis. So if our matrix is m by n, meaning m rows and n columns, then what would the runtime of this binary search be?
So potentially you could have to check
all rows. Yeah, each row you would have to check, and then for each row, it's log of n.
Log n, yeah.
Okay, fine. So going back to our hypothetical problem where it's sorted from top left to bottom right, right? So it's sorted, so this guy is bigger than this guy, and this guy is bigger than this guy. So if we had that kind of matrix, then what would the runtime of the binary search be? So we said, so first you identify which row the target should be in, right? Yeah. So how long would that take?
I feel you could maybe eliminate rows faster if this was all like sorted continuously.
Because so in order to identify which row the target is in, you just need to look at the first column, right? So you just do a binary search on the first column, which is log of m, right? The column has m entries, right? Then once you identify which row it's in, let's say it's this row, then you do another binary search in this row, right? And this takes log of n, right? So this would be your total runtime. Okay, if this matrix were sorted from top left to bottom right, which is not the case in this problem, right? But there are some other versions of this problem where it's sorted like continuously, then you can use binary search. And this is good, right? Log m plus log n. Equivalently, you can say, another way of looking at this would be, I'm not going to first identify the row, then identify that target, find that target, try to find that target in that row, I'm just going to divide this matrix into, two halves, right? So yeah, so basically, your middle point will be here, right? This will be your middle point. Then, you can do some like arithmetics to figure out, you can basically, you're doing a search from 0 to m times n, right? -1, right? This is the entry of the index of this is m n -1. This is 0, right? So yeah, so basically you're doing a binary search on m times n elements, right? So which is log of m times n. And this is actually equal to log m plus log n, right? So this is equivalent to the previous one, where you first identify the row, then you identify the column, right? It's the same as just doing just one giant binary search on all of the entries. Okay, now let's move back to our original problem. So yeah, we mentioned that we can do binary search and it would take m times log n time, which is not bad, right? Now, if they say, okay, what if m is like much bigger than n? Then what do we do? I mean, then in that case, you can do a binary search on the column, right? So you can say, so yeah, so what does it mean for m to be much bigger than n? Well, that means that your matrix will be super like thin, right? So it has many. This is m, this is n, right? So we said that, okay, if you're going to do binary search on each row, then this is m times log n. But this log n is not very helpful, right? Because n is already small, right? Because if the interviewer says, well, let's assume that m is much bigger than n, then doing log n doesn't really help much, right? Because n is already small. So n from n to log n is not super helpful, whereas m can be super big, right? So you actually want to convert m to log n, right? So I mean, how do you achieve that? Well, you can just do binary search on every column, right? You say, oh, is the target in the first column? I do a binary search, right? Is the in the second column? I do a binary search, etc., right? So how many binary searches do I do? I do n binary searches, right? And in each binary search, I'm scanning the entire column, right? Which contains m items, right? So you would do this. Okay. Now, can we do better than this though? If both m and n are big, can we do better than this?
Can we do would that m plus n? So if we walk down the hill, if you draw the left, yeah. So if we start from the 15, we can still use binary search actually on the row. So we go using binary search, we discover that 7 is the first biggest number, more than 5.
Okay, so you're here, then you're like, okay, so you discover that 7, you would come here, right? You will come here to 7 because 7 is the smallest number that's at least 5.
Yes, the smallest number bigger than 5.
Okay.
And now I have to go down. So I go down to 8.
Okay.
And now 5 is less than 8, so it has to be on the left of that. And again, we can do a binary search on the left side of this. And we arrive at the 5.
Okay.
So we are doing the same, like we're doing binary search on everyone. In worst case, it might be the same, but in many cases, it will be better because.
So okay, so I don't feel that binary search in this case is necessary though. I think during the interview, if you try to implement that binary search, I think it's just going to take you a lot of time without gaining much. Okay, let's try to figure out a linear time solution then. So the linear time solution is you start. I like that you're starting at the 15. Okay, you're starting at the 15. You always start at the top right corner. Okay, and you say our target is 5, right? So currently 15 is obviously too big. Okay, 15 is too big, so I want to go smaller, right? Now when you're at 15, you have 2 ways to go. You can either go down or you can go left, right? Remember, the columns are sorted, right? So if you go down, you are increasing the value, right? You definitely don't want to increase the value. You want to go to 5, so you want to go to a smaller node, a smaller cell, right? So that's why you go left, and you're at 11. Now, when you're at 11, still you want to go smaller, right? So you go left, and you're at 7. Remember, at each step, you have 2 ways. You can either go left or you can go down, right? Going down means you're increasing the value. Going left means you're decreasing the value. So the direction depends on whether your current cell is too big or too small, right? So when you're at 7, still 7 is too big, right? So you go left again, and then you actually reach 4. Okay, now when you're at 4, 5 is bigger than 4, right? So you want to go down. So now here you manage to you've managed to find 5. Now let's assume that the target is like 0. Let's see what happens. Actually, let's say that the target is 6. Okay, let's assume that the target is 6. See what happens. All right. So when you're at 5, 5 is smaller than 6. So then you go down, right? So then you that's how you can find 6, right? So okay, let's see what happens if you give it something that's not in the matrix. Okay, let's say you are looking for okay, let's say you're looking for 18. Okay, let's see what happens then. So okay, so you're at 15. 18 is bigger than 15, so we should go down, right? So we're at 19. 19 is too big, so we go left. 12 is too small, so we go down. And 16 is small, we go down. 17 is also small, we go down. 26 is too big, we go left. 23 is too big, we go left. 21 is too big, we go left. And yes, and therefore we have found 18, right? Now, oh yeah, so okay, so instead, if we were looking for 25, let's see. Actually, yeah, 25. Okay, so then let's see what happens, right? So when you're at 26, 25 is too big, right? So you want to go smaller, so you want to go down, but 26 is already at the bottom row, so there's no way for you to go down, right? And in that at that time, you just return false, right? Okay, now let's see. What if I wanted to find 0, right? 0 is obviously not here. Let's see what happens when the number is too small. So 15. 0 is smaller than 15, so you go left, and smaller than 11, you keep going left, right? You keep going left. You're at 1, but 1 is too big, so you want to go to the left, but there's no way for you to go left, and that's why you return false, right? So basically, you return false if you have either reached the bottom row or the leftmost column, and still you haven't found it, right? So what would a runtime be? Remember, at each point, you have 2 decisions, right? If it's too small, you go down. If it's too big, then you go left. If the current cell is too big, bigger than the target, then you go left, right? So, and eventually you're either going to hit, well, here, right, here, or you're going to hit here.
Is it m plus n?
Yeah, the total runtime will be m plus n, right? So, yeah, it will basically look like this, something like this, right? This is the worst case. Okay. Any questions about this approach?
So what is better? The previous one you showed was O log base m log base 2n, right?
No, the previous one was the
M
binary. The binary search one was O of m times log of n. This one is m plus n. Which one do you think is better?
It depends on the size of n actually. So if n is large, then actually the binary search one will win.
If n is large, okay, yeah. Now, usually, yeah. So usually we assume that m and n are like comparable, right? If they're comparable and if like they're like both large, right? If they're both large and they're like equally large, then this is like, to be precise, this is actually max of mn, right? Now, if m and n are the same, then this will just be O of m, right? But here, this will be m log m, right? So we would say that, if m and n are like about the same, then this would win, right? Now, if it's either too thin or too fat, then actually this would win. This or O of n log m, right? We have talked about this, like you would choose to do a binary search on column or do a binary search on row, depending on the shape of the matrix, right? You can, you can think about it if this is like a super fat matrix where you only have just like, a very wide matrix where you only have like one row, right? But the row is super long. Then of course a binary search is just super fast, right? But our linear approach would be, okay, this is too big, then we keep going left, right? We keep going left. So in this case, obviously binary search would win, right? Similar to just where you only have one column and this column is super long, right? Of course, binary search would win.
So can you explain on the previous slide? Go back one more. Sorry. Yeah, here. So why is m plus m equal to max mn?
Okay, so O of m plus n is equal to O of. Okay, so okay, you can think about it. So if m is bigger than n, what is m plus n here?
If m is bigger than n, was
this will be O of m, right? But basically, this n term doesn't even matter. right? This is the definition of O. Big O is, this N is
I see, 'cause it's not-
overshadowed by
'cause it's not
M.
Because it's not the dominant term. Okay.
Yeah. Right. And then similarly, if M is smaller than N, what would M plus N be? This will be dominated by N, right? So that's why we have this. Okay, any questions? All right, this trick is very, very useful if our matrix is sorted row-wise and column-wise. Now let's look at another one.
So we can do the same climbing down the hill algorithm, right? So we start at top left or top right. And if we have, since I see -1, and since if it is like, suppose just to make it more interesting, we can make the top right one 1.
Okay.
So if I see a positive number, then go down till you see a negative number.
Okay.
So go down. And now whenever I see a negative number, I keep going left till I see a positive number.
Okay. Then you go down.
Yeah, then go down because I see a positive number. And now because I see a negative number, so go left. Then again go down. And now go left and try to go left.
Okay, hold on. So previously when you were at -1, you go left. Okay, so now when you're at -1, you go left. Okay.
Yes,
so
correct.
here.
Yeah.
Okay.
And we try to go left again, which doesn't work out.
So yeah, so I mean, we want to return a number of negative values.
Okay, so every time that we are going down, so every time we are going left, we have to count off a certain number of negatives, which is given by the index. So the first time when we moved left, then we went from index 3, the column index 3 to column index 2. And we found our last positive at column index 2. So the number of rows -2 plus 1 would be the number of negatives encountered. So we have encountered one negative.
Oh, okay. So basically you record sort of remember the number of negative values at each row.
Yes.
Right. So basically, initially you're at this 1, right? And then you move down and you're at this -1, then you go left and you see a 1. So anytime you see a positive number, then the first number, I mean, the positive number means that everything to the right of this positive number is negative.
Correct.
Right. So, so basically, that there's one negative value on this row. Then you go down and you're at this -1, right? Then you go left and you see, oh, okay, so this is my positive number. So I know that everything to the right of this 1 will be negative, right? So you know that there are 2 negative numbers here. Then you go down, you see a negative value, and then you go left, you see another negative value. I mean, you try to go left, you can assume that this will be a a non-negative number. So you know that everything to the right of this, will be negative.
Yeah, actually, this last one is a tricky end case, because you're going, if you have many negative numbers and you still keep going left because it is last row, is there like, can we do a dictionary thing? So if we make a dictionary in which we are capturing the number of negative numbers. And
sure.
And
what will the key be?
The key will be the row number.
Okay.
And the value is the number of negative numbers. So initially this is empty. And every time we go left, we have the current index, and we know that everything to the right of that is negative. So we do the max of whatever is for that row number in the dictionary right now, and the current column number. So and the total number of columns minus the current column number.
Yeah, okay, but we can just record that, like we can just add that to our final result. Why do we need to use a dictionary to store it?
Yeah, that last case is a little tricky to code. The one in which we have -1, and again, I don't want to double count the rows, the thing when we add, right? We'll have to put if else's for that. Right?
I don't understand. Okay, so I don't think that you need to do any special case just because it's a last row. I mean, I was able to implement without doing any special handling. Okay, so first, does everyone understand the algorithm? Right, so we add to our result every time when we're leaving the current row. Because when are you leaving your current row? You will stay on the current row if you're currently at a negative cell. Right here, for example, you're at the negative cell, so you will not leave your current row. You will go left. You only leave your current row when the current cell is positive, well, it is non-negative. Then you would go down, right? You would leave the current row and go to the row below it. So anytime when you're leaving the current row, the length of the row minus your current column. For example, when you're at this 1, right? Your column is 1, like this is 1, right? So the number, so basically, 4 minus 1, 1 plus 1, okay, is 2. I mean, we're using 0 index, right? So the column is 1, but that means that there are 2, you have 2 numbers before or equal to it, right? So that means that, well, 4 minus 2 means that there are 2 numbers to the left, to the right of you. And we know by construction that the numbers that are to the right of you are all negative.
Okay, quite. So there can be a case where like we should like go to the right for finding the negative number, right? So can there be a case like more than?
You mean like, why are we only moving down and left?
Instead of -1 over there, yeah, it can be a 0, right? 0. Yeah.
But then this can totally be a 0.
Yeah, then we need to like go to the right and then find the negative number. And
well,
then we will be coming back.
Well, so you would, okay. So if you were at this 0, right? So initially you start from the, let me actually use a different color here. Okay, so you start from here, right? Okay, this is a 2. Okay, so this is a -2. Okay, so you start from 1, right? Now, okay, so then you would go down, right? You will go down to this -1, right? And then you will go left, you will go to this 1, and you will go down to this 0, right? When you're at this 0, you will go down to this -2, right? Then you go left to this -1, and then you go left to this -1.
Okay, so as we have -1 in the previous element, we can just consider that the same length can be also here in the next one.
Yes. Yes. So then what is the final result, right? If you should look at what is the index at which we have left the current row, right? So, we left this row at here, right? So, basically this is the 3rd number in this row, which means that there's only 1 number to the right of it, right? 1 negative number to the right of it, right? Now we have left this row from here, right? This row from here. So still that means that there's only 1 negative number to the right of it. Now we have not left this last row, right? So that means that, well, like everything on this row are negative. Okay, does anyone want to implement it for us? Alex, do you want to implement it for us?
Yeah, just give me a moment.
Yeah.
To share the screen. All right. So what do? We just traverse it from top right to bottom left, right?
Mm-hmm.
All right. So we'll have main loop, which goes through the rows, and on each row we'll have column. And this column variable we will resort. So we will not reset it to 0 every time or to amount of our columns every time. Yeah, it will persist. So all right, so here we just go from right to left until we hit first negative number, right? Or until we just
let's not use a while loop. I think it's cleaner if we say, okay, if it's too big, then we go left or something. If it's too small, then we if it's negative, then we go left. If it's not negative, then we go down. I think that's cleaner.
But this is the same, right? I mean, here we go down every time when we are finished with while.
That's also fine.
I'm just not sure about that your approach that you mentioned.
So I wanted to say, I mean, that's fine. You can go ahead and implement your way.
Let me just finish this, right? Then we do your way. Let's just see if I manage to finish it quickly enough.
Yeah.
Maybe we'll start for a while. So, all right. So right here we are on a positive number, right? So let's say it's so now our C column counter points to here. So we need to add 1. What do we add here? So yeah, I believe that's the way. But let me just double check it. So in this case, length is 4. C points to 2, and we need to get, as our result, we need to get 1, right? So in order to get 1, we need to do 4 minus 2 and minus only 1. Okay. So, and if we had something like this, our C would be here. So we would have 4 minus 0 minus 1. Yeah. And if our C was here, minus 1, we'll have 4 minus 1, which is plus 1. Minus 1, it would be 4. Okay, cool. So this seems right. Yeah, that should be it. Right. Oh, of course. All right. Yeah. I thought it would be harder.
Okay. Good. Yeah,
so
this is good.
Yeah. So what was your algorithm? Do I need to re-implement it the way you said? I just
no. This is good. This is good.
Okay. Cool.
This is good. Okay. Any questions, anyone? Okay. So yeah, this is very good. This is a linear time solution, right? Again, like, you know, if you're not familiar with this approach, then you can do binary search, right? You basically you will be, and the runtime is the same as the last problem, m times log n. Okay.